Use the following information to determine the function f. So notice we are given a derivative function. So the function that we're looking at here is a derivative, and we're asked to find the original function f. So that means we're going to be computing an antiderivative. Now, since the original function was marked as a derivative function, then this is a case where we do not need to use a capital F of x to represent the antiderivative. We'll just use f of x because the original had the f prime notation. We'll just use f of x for the antiderivative. So we have a coefficient of a 6, so we'll leave our coefficient of a 6. And then the antiderivative of the x squared term, remember we're going to use the antiderivative power rule, essentially, where we add 1 to the exponent, so that would be an x cubed, and then we will multiply by the reciprocal of 3, which is 1/3. So the antiderivative of x squared is 1/3 x cubed, minus the antiderivative of 6x. We'll leave our coefficient of x, compute the antiderivative of x to the first power, which would be 1/2 x to the second power. And then the antiderivative of a 1 will just be x, and then plus a constant. So this is our general antiderivative. So if we simplify, our function will be 6 times 1/3 is 2x to the third power, minus 6 times 1/2, which is 3x squared, plus x plus c. So this is my general antiderivative. But then notice the additional information that you have been given. We've been given that f of 1 is equal to -7. So we have a specific value. When x equals 1, we know the value of the function is -7. And this is going to allow us to solve for the constant and find a specific antiderivative instead of the general antiderivative. So essentially, think of this as a coordinate. When we say f of 1 equals -7, that means we're giving you one of the points on the original curve, 1, -7. So when the y value is -7, that means that the x value was +1. So we'll substitute in 1 for all of our x values, and then -7 for our y value, essentially. So I'm trying to color code for you and plug in 1 here for our x values. And then that means that we will be able to solve for c. We'll solve for our constant. So -7 will equal 2 minus 3 plus 1 plus c. So that ends up being that -7 is equal to our constant. So now we can write the specific function, so this is the specific antiderivative, instead of the general antiderivative, which will be 2x cubed minus 3x squared plus x minus 7, since 7 was our constant. Okay, let's move on to our second example here, where our derivative is 4 divided by 1 plus t squared. So this derivative is in terms of t this time. So again, we'll compute our antiderivative. So the antiderivative would be our function f of t. Now it may help you to first think of this derivative function that we're given, f prime. Think of this as 4 times 1 over 1 plus t squared. So the 4 is really just the coefficient in this case. So therefore, my antiderivative will contain a 4. And then we just have to think about what the antiderivative of 1 over 1 plus t squared will be. And that's one of our derivative rules that hopefully we have memorized. It turned out that inverse tangent had a derivative of 1 over 1 plus t squared. Therefore, the antiderivative would be the inverse tangent of t. And then plus a constant, because again, this is the general antiderivative. So now, if we continue to look at the additional information that we were given, which is f of 1 is equal to 0, think of that as a coordinate. When x equals 1, y equals 0. So we have a coordinate on this original f of t function. So let's go ahead and substitute in 0 for y and 1 for t. So 0 equals inverse tangent of 1 plus our constant. And then we can solve for c. Now in this case, we do need to think about a little review of trig here. So when we're computing the inverse tangent of 1, remember that means we're asking ourselves to find an angle. So we are finding the angle, basically, that has a tangent value of 1. And that angle would be pi over 4, or 45 degrees. We're going to leave our answer, however, in radians. So 0 is equal to 4 times, so the inverse tangent of 1 is going to be pi fourths. Again, because the tangent of pi fourths is equal to 1, plus our constant. So we end up with 0 is equal to pi plus c, so our constant ends up being negative pi. So substituting that back into our function, we now have our f of t function, which will be 4 inverse tangent of t minus pi. So again, this is a specific antiderivative rather than a general antiderivative. Now let's look at one last example. This example is different than the previous two because we're given the second derivative this time. Yet the directions are still the same. We are still trying to find the original function f. So if we're given the second derivative and we compute the antiderivative of this function, then that means we will be working backwards to the first derivative. So we first have to go from the second derivative backwards to the first derivative, and then we'll go backwards one more time to get back to the original function. So it's like we're taking the antiderivative 2 times. So let's start with the antiderivative of 2e to the x, which will just be 2e to the x. And then the antiderivative of 3 sine of x, so I'm just going to leave the 3 and let me think about the antiderivative of sine of x. So we know that the derivative of cosine of x is equal to negative sine of x. Therefore, if we want the antiderivative of a positive sine of x, then that would be a negative cosine of x. So be really careful with your signs there. And then we need a plus c, because again, this is going to be a general antiderivative. So right now, my first derivative, f prime, is equal to 2e to the x power minus 3 cosine x plus c. Now on the previous two examples, we were able to use a condition that was given to solve for c. But notice, look at the two conditions we were given in this example. We have f of 0 equals 0 and f of pi equals 0. So in terms of coordinates, these are both coordinates on the original curve. They're not coordinates on the derivative. So again, these two pieces of information basically correspond to ordered pairs, 0, 0, and pi 0, but these are ordered pairs on the original curve f of x. These are not on the f prime or the derivative curve. So right now we're not going to be able to use either of these coordinates to help us solve for the constant that's in our derivative function. So we're just going to leave it as plus c. So now that I have my f prime function, I'm going to compute the antiderivative one more time, which is going to allow me to work backwards to the original function. So the antiderivative of 2e to the x will also be 2e to the x. Then I have a negative 3 as my coefficient, and I can think about what the antiderivative of cosine is. So the antiderivative of cosine is going to just be sine of x, because remember the derivative of sine of x equals cosine of x. But now we have this constant that we also need to compute the antiderivative of. So remember, if I had previously given you, let's say, a derivative of 4 and asked you to compute the antiderivative would be 4x. And that's because with every constant, you really have an x to the 0 power. So when we add 1 to that exponent, we realize that the antiderivative would have an x to the first power. Well, this is any constant c. Therefore, the antiderivative of any constant c will be c times x. But then we need another constant for our general antiderivative, And this is where I don't want you to use c again, because if we use c, then we're implying that these two constants are the same, and they may not be the same. So you have two options. You could either use a subscript and call one c sub 1 and one c sub 2, or I prefer to just go ahead and move down the alphabet, and I just call my next constant d. So right now, what I have for my original function is f of x is equal to 2e to the x power minus 3 sine of x plus some constant c times x plus another constant d. But now I'm ready to go ahead and use the two coordinates that I was given initially, and we can substitute those in, and this will allow us to find our constants c and d. So let's go ahead and start with the coordinate 0, 0. So if I substitute 0 in for y, as well as 0 for all of my x's, I'll have this equation: 0 equals 2e to the 0 power minus 3 times sine of 0 plus a constant times 0 plus d. So e to the 0 power is 1, so that'll leave me with 2 times 1. Sine of 0 is just 0, so negative 3 times 0 is 0, and our constant times 0 is 0. So I'm left with 0 is equal to 2 plus d. Therefore, my d is equal to negative 2. So this allowed me to get one of my constants. So now let me write what my function looks like with my new d value. So f of x equals 2e to the x minus 3 times sine of x plus cx minus 2, now that I have found d. And now we'll go back to the original information given to us, the second piece of information, which was f of pi equals 0. So that corresponded to the coordinate pi comma 0. So we'll go ahead and substitute in 0 for y and pi for x. So when y is equal to 0, x is equal to pi. So 0 equals 2e to the pi power minus 3 times the sine of pi plus c times pi minus 2. So at this point, sometimes it's difficult to remember what we were trying to do, what our goal was. So just a reminder, our goal right now is to solve for the constant c. So if we simplify, we have 0 equals 2e to the pi power. Remember, the sine of pi is 0, so negative 3 times 0 is just 0, plus c times pi minus 2. So if I'm solving for c, then I need to subtract the 2e to the pi, as well as add the 2 to the other side. So that will equal c times pi, and then I can divide both sides by pi to isolate the constant. So my constant will equal negative 2e to the pi power plus 2, all divided by pi. And this is the value of the constant in its exact form. Of course, you could put this in your calculator and get a decimal approximation. So now that I have my constant, I can go all the way back to my original function. I can substitute that value in and actually write my final answer. So my final function is going to be f of x is equal to 2e to the x power minus 3 times the sine of x plus the constant we just found for c, which was negative 2e to the pi power plus 2, all divided by pi. And that was our constant that was being multiplied by x. And then we have our d value, which was minus 2. So this would be my original function written in exact form.